Okay, so there's my talk. What can I do with a maths degree? So what I want to do is give you some idea of the sorts of careers that are open to you for a maths degree. And there's me, Chris Good, and I'm a senior lecturer here in pure mathematics. So how many of you are currently studying maths AS or A level? Everybody. Excellent. Okay. And how many of you thinking of going on to university to do mathematics? Okay. What about physics? Engineering? Medicine? Couple? Anyone? Anything else? Anybody doing anything else? What are you going to do? Economics. Okay. Yeah, economics. Another one. Okay. So I'm not going to try and persuade you not to become physicists or engineers or doctors, because clearly, just as the country needs mathematicians, it also needs physicists, engineers and doctors, economists, and so on, biologists, all of those things. But what I want to do is give you an idea of the sorts of careers that are open to you if you do decide to do a degree in mathematics. So what can a maths degree What can you do with a maths degree? Short answer is pretty much anything. Okay? You can't become a doctor after a maths degree. You do need to go away and do a degree in medicine, obviously. Other than that, though, you can pretty much do anything you like. We have mathematicians here whose work is so closely related to engineers that they collaborate with the engineers all the time. They don't maybe do the experiments, but they do the kind of mathematical side of what the engineers are doing. So here's how I'm going to run this talk. So I wanted to talk a little bit, very briefly, my view at least, about the difference between A-level maths and university maths. And then I thought it would probably be worth saying what just a good degree should give you. And then what about a good maths degree? What will that give you? And then I'll list some possible careers. And this is a pretty ad hoc list that I made up. One time I was giving an admissions tutor's talk, and I just thought back about all the people that I'd known over the years and what they'd gone into. Some of them, these things are obvious, some of them are less obvious. I'll mention a little bit about why you should believe me at the very end. And throughout, what I'll do is I'll give a few examples of what sort of mathematics you're going to be using in particular careers. So I'll just pick those. I made a list of things. I brought some recent stuff from Scientific America. No, this is New Scientist, actually. I might mention something I heard on More or Less on the radio yesterday as I was sitting in the car, that sort of thing. So we'll just pick some ideas. So first of all, I'm an example of somebody who did a maths degree and has a career out of it. I'm a mathematician, so I thought it might be worthwhile just explaining what I do. So part of the time I lecture to first years. I currently teach the first year calculus course when we start dealing with integration and differential equations. I do a third year general topology course. The other half of my time, when I'm not being an administrator, I do research. So what am I doing? I'm looking at new areas of mathematics. I'm trying to discover new things about the mathematical universe that's out there. And those two things are in the area of topology. So topology, various different sorts of topology. I tend to think of topology. The classic thing is rubber sheet geometry. What is it that makes this cup the same as a plate, but not the same as a donut or a teacup, which are also the same? And it's because you can pull the one into the other without breaking or tearing if it was made out of rubber. I'm more interested in the sort of topology I do, set theoretic or general topology, the properties of space. So here's an example of a theorem from, well, our undergraduates do this in their second year. So we need to know what a continuous function is. A continuous function. Well, actually, it turns out the definition's pretty daunting when you write it down for the first time, and most of our undergraduates go, ouch, that looks really horrible, and run a mile until they get used to it. But roughly speaking, you can draw it. You can draw the graph without taking your pen off the paper. Okay, that's sort of the definition. And then what you do is you turn it into math language and you get something that I won't write down now because I don't want to frighten you off from doing a maths degree. But, so, here is a fact about continuous functions. Let me give you an example first. So, here's the x-axis and the y-axis. Here's 1 and here's 0. If I draw the graph of y equals 1 over x, what do we see? We see that it starts at 1 here, and then the closer we get to 0, we're dividing by a smaller and smaller number, so the graph shoots off to infinity. This function is continuous because I've drawn it without taking my pen off the paper. But it's continuous on what we call the open interval, 0, 1. So I have excluded, in particular, the value 0 here. And what's happening is that the function somehow has the room to shoot off to infinity. Because it can't be, there's no number, 1 over 0 is not defined. So now, what happens if I try and draw a continuous function between 0 and 1? Okay, now I'm going to draw any continuous function. So let's think about some function. I don't know what its equation is. I don't know even that I can write down an equation for it, but I know it's continuous. But now I'm going to insist that I have a value at 0 and at 1 and everywhere else in between. So I'm going to include the endpoints of this interval. So if you've seen this notation before, we would use square bracket notation. So now what happens? Well, the function will have some value at 0. I don't know what that value is. Let's put it there. And it will have some value at 1. Somehow, I've got to draw the graph of this thing without taking my pen off the paper, and I've got to start here and end up there. So whatever I do, no matter how high I try and get up there, I don't have room to tend off to plus infinity or tend off to minus infinity. So over here, when we don't include the endpoints between 0 and 1, we don't include the value 0 and we don't include the value 1, my function somehow has room to tend to infinity. Infinity's bad. Black holes, centre of a black hole, physics breaks down, we've got a singularity. We have problems. Over here, if I include the endpoints and all the points in between, my function can't tend off to infinity. There's no room for it to do that anymore, somehow, even though I've included more values. It turns out that this is true for any continuous function. If I include the endpoints of my interval, it's true for any continuous function. So I can instantly say that I don't get any singularities, I don't get any bad behavior. That is a property of the space that the function was acting on. It's a property of the x values rather than the function itself. I only needed to know the function was continuous. I didn't need to know anything else about it. Here, slightly different space, at least one function, and in fact lots of different functions, continuous functions, can behave badly. So the space can force the functions that you're looking at to behave well. Okay, so that's what I mean by topology. I'm interested in what happens to the space, what's the space doing, the set of points that the function's acting on, rather than the functions themselves, in some sense. The other thing I do, and I did have a nice little computer program called GeoGebra, if you've seen it, excellent little dynamic tool to look at mathematical ideas. Unfortunately, it's not loaded on this computer, and I can't get the thing to work. So, dynamical systems. I'm interested in iterations of functions. I have a function, I input a value, I get the next value out, I put that value back into the function, I get the new value out, I put that value back into the function, get the new one out. Think of a population. I've got a field, I've bung some rabbits in it. Each generation I get a new set of rabbits, count how many rabbits there are. That will determine how many rabbits there are in the next generation. If there are too many rabbits, they will eat all the grass and a lot of them will die. If there are too few rabbits, they've got lots of food, so all the babies will survive and the population will grow. How does that behave as we run time forward, as we run generations forward? Turns out that even very, very simple models can end up with things like chaotic behaviour. So the number of rabbits we have at any given time appears chaotic. So I'm interested in how we spot things like chaos. What do we mean by chaos? What's the difference between chaos and random behaviour? Chaotic behaviour is determined, though it might appear random, it's determined precisely. Random behaviour, think of radioactivity and that sort of thing, throwing a dice. So that's the sort of thing that I'm interested in. I do have a picture of the Mandelbrot's. Ooh, okay. There we go. So the picture of the Mandelbrot set, why is that related to dynamics? Well, we have a very simple equation of complex numbers, but we do what I just said. We take an initial value, we square it, we add some number c to it, throw that back into the equation again, square it, add a number c, square it, add a number c, square it, add a number c. See what happens. In the black bits, it stays bounded. It doesn't tend to infinity. In the coloured bits, it shoots off to infinity at a particular speed. Depending on the colour, it determines the speed. So a very simple equation, admittedly of complex numbers, which you'll meet at university or maybe in further maths if you're doing further maths. A very simple equation gives rise to this fantastic object here, which was only spotted when we started having the idea that we could have such fantastic and complex pictures arising from something very simple, only really appeared to people, to Benoit Mandelbrot, who died earlier this year, I believe, once we had computers to be able to spot this thing. So lots and lots and lots of new mathematics arising from something that we hadn't expected, hadn't even thought about happening. Okay. So that's what I do. So that's a career that you can do in mathematics. So basically, I get paid to get out of bed and do the thing that really turns me on. I have problems that I really want to solve. Might make me a bit of a geek, but that's what motivates me. And it sends me all over the world. I've travelled to Oman, to Texas, to New Zealand, to Australia, to Czechoslovakia, to Mexico, to work with people on this sort of thing. Okay, so what about A-level maths versus university maths? Well, let's have a big difference. At university, ideas come more quickly. Okay, you have to keep up. You're probably studying maths if you're doing a maths degree, or maybe maths with another subject. There's probably more emphasis, although, as Joe has wrestled with, what do we mean by a problem? Possibly more emphasis on problem solving rather than answering questions. So more emphasis on problems where you're not quite sure where the answer might come from. You've got to experiment a bit. More emphasis definitely on explaining your ideas, explaining your solutions more clearly, logically, writing in English sentences. So here's there we go. So this is a paper. I just chose a random paper. And as you can see, there are some formulae in there, but mostly it's sort of text. I don't expect you to dive right in and read that. But it's written in English because we're in Britain. And it's written in sentences, paragraph sentences, and so on. So more emphasis on explaining your ideas, not just solving the problem, explaining how you solved the problem. More proof. So at university, more emphasis, particularly as a pure mathematician, I tend to emphasize that more. So more emphasis on proof. Why is what you've written down actually true? Why is it always true? Why could it be nothing else? Chance to get to the boundaries of research, a chance to get to see, at least understand what on earth I was talking about in that paper that I just put up there. It's harder, but it's fascinating and rewarding, and that effort is worth something. And I kind of like to think that A-level's sort of training camp. A-level's where you learn how to kick a football, how to swing a tennis racket, learn your scales, all that boring stuff that you have to do before you start getting to the exciting stuff. Now, that's not to say that A-level's boring, right? Because you wouldn't be doing it if it was boring. But when you get onto university, you start to see some really exciting stuff. That's when you can start to put it into anger. All that training starts to pay off. So A-level, the training camp, university is where you get to play the game. So how does maths help? So I wrote down a bunch of things here. Just sort of, let's put them all up. Okay. Let's do submarines and bubbles, because that's something that used to go on in... So defence research. So a few years ago, some of my colleagues here were working on submarines and bubbles. Why are they working on submarines and bubbles? Well, here's a submarine. Submarines are dangerous, right? When you're in a boat, they tend to shoot missiles and things and destroy torpedoes. They also tend to shoot nuclear weapons as well. So you might want to destroy enemy submarines. You might want to protect your own submarines. So how do you destroy a submarine given that it's hidden under the water? Well, here's what happens with a bubble. If I form a large bubble, some depth in the water, there we go. What happens? Well, if it's large, there's going to be there's going to be a pressure differential between the top and the bottom. So the pressure is greater here than it is here. So as time evolves, what's going to happen is that the water is going to try and fill this bubble here. So the water will start rushing into the bubble, but from below. So this is like a fist of water that's going to fire upwards, possibly with some velocity. And if it's going fast enough, if you've ever used a cartridge yet to clean a patio or something, you can see that water moving very fast is a powerful thing. So what happens if you drop a depth charge underneath a submarine? One way of thinking about it is that you have a bubble, and the bubble starts to decay, and it decays by forcing water in from the bottom, so you get a jet of water rising up, hitting a submarine, possibly, and cracking it, breaking it. So submarine manufacturers are very interested in the dynamics, how you model bubbles. What happens with a bubble? How does it work? How do you design your depth charge so that this sort of thing will happen appropriately? How do you design your submarine so that it can kind of withstand the attack? Okay, so there's one example, defence research. So what does a good degree give you? The ability to work and think independently. The ability to learn and research new ideas by yourself. That's why you want a degree. That's why people employ you, majority of you, because you've got a degree, because you can go away and think by yourself. You don't have to be told what to do. Self-motivation. You have to be motivated to spend 3 or 4 years studying something, one thing. Time management. You've got to work out when to hand in your assignments and so on, when to do your revision, all of that sort of stuff. Confidence. You know, you're qualified, you've got a degree, maybe you've gone to a further degree, you've got that confidence that you understand something as well as many, many other people in the world, if not better. This is a great thing. Sasha Borovic, he's a professor of pure mathematics at Manchester University. He's formulated this, I believe it's his, it is his, isn't it? This law of excessive learning. So his idea about a degree is, a degree teaches you more than you'd ever need to know. Most of you are, you know, even if you do a maths degree, you're not going to go on to be mathematicians, you're going to do something. How much maths do you need to know? Well, more, if you know more maths than you ever need to actually put into practice, in anger, then you'll know enough, you'll be confident enough with the mathematics you do know to be able to use it fluidly and simply and understand it well enough. Okay, so if you're a teacher, you have a maths degree, you're not teaching that material to your A-level students, but you've learned so much more maths that you understand the material you're teaching at A-level that much better. So the law of excessive learning. Employability. Employers like people with degrees because it proves something about you. It proves that you're self-motivated, proves that you can manage your own time, proves that you can learn and work independently. And a degree is worth something like 150k extra earnings over a lifetime if you compare yourself with somebody else. What about a good maths degree? Well, in addition to all of the stuff above, you will learn how to formulate problems. So the first thing you might want to do with a problem, when faced with a problem, is to formulate it, to understand what you really need to do to solve the problem. And then you might even be able to solve the problem. Okay. I believe it's true that certainly a few years ago, NASA, on any committee that they set up, they would put a mathematician or a theoretical physicist, precisely because even if they were talking about how to extract more money from Congress, what it told them to do was, what the mathematician allowed them to do was to work out what the real problem was and how to at least start attacking it. So how to formulate problems and possibly solve them. You learn how to follow complex technical arguments. That's what we do. We argue in a highly technical language sometimes, but we argue about things and you learn how to follow those, criticize them, create your own arguments, and in doing so you learn how to use technical language, express complex ideas clearly and logically. That's also something that employers like. Even if what you're trying to explain has nothing to do with mathematics, the ability to explain complicated, difficult ideas, policy documents, formulate arguments, formulate approaches, attack strategies for a business problem or so on, you're able to run through those complex, difficult, potentially ideas and explain them clearly and logically. I think we're making all of these slides available, aren't we? So you don't need to take notes. They'll be up and available at some point if you're getting left behind. Obviously, you will learn some specific mathematical knowledge, perhaps some calculus, some analysis, some linear algebra, simultaneous equations, modelling of phenomena, probability, statistics. So some mathematics you'll obviously learn in your maths degree. And you'll gain skills, analytical skills, statistical skills, computational and computing skills, those sorts of things. So specific skills that maybe employers want. You'll have even greater employability. And on average, you will earn about 225,000 extra over a lifetime. So, what was it? 150, so a significant extra bit. What does that tell you? Well, engineers also earn that sort of money extra. Medical students do. It's the poor arts graduates who are making up the difference there, who earn less, possibly, than their student loan extra over a lifetime. But let's not go into that. Right, how does maths help? Let's do something else then. Let's do telecommunications and error correcting codes. So here's an example of where mathematics is used. Let's take a very simple example. Let's suppose that, so I've just bought a house. So I've just spent more money than I care to think about. And at some point, my partner and I had to get on the phone and she's saying, well, are we going to buy it? Yes, no. So at some point, I have to, on the phone, send the message either yes or no, to whether we're going to make an offer, sign the contract, commit ourselves to years of penury. So I need to send a message, yes or no, buy the house, don't buy the house. It's quite important at certain points when you do this, it's quite important that you send exactly the right message because otherwise you're liable for 10% of the value of the house or something, which in our case is a lot more than I can afford to throw away. So I need to send a message, yes or no, to Jenny. So I need to send a message to Jenny, yes or no. Jenny lives in Brighton. I currently live in Oxford. I work in Birmingham. So I spend a lot of time in the car. So I'm doing this over a mobile phone network. So I have to send yes. Well, maybe yes is 1 and maybe no is a 0. So I have to send this message over a channel. And I don't know if you've tried to drive along the M40, around the M25 and down the M23. There are places when your mobile phone signal breaks up. So there are times when there's noise in the signal. And maybe the little beep that says 1 is distorted so that it sounds like a little beep that says 0. That could be a problem. I could be signing a contract that says I want to buy something I don't want to buy, or vice versa. It could be worse. It could be, are we going to bomb this set of tanks or not, when we're under, in a very kind of fluid situation. So we need to make sure that these messages get through. Well, suppose there's a... here's one way of thinking about how to get around this, and there are lots of much, much more clever ways, but here's quite a simple way. Suppose the probability of distortion is, let's say, a quarter. So the probability that the 1 comes out as a 0, or the 0 comes out of a 1 due to some static, due to some breakup of the signal because I've gone through a black spot on the motorway or whatever. Well, in that case, if Jenny receives a 1, how sure is she that I actually said yes, or maybe I said no? Well, how often does, with a probability of a quarter? That's a lot of, that's a lot of probability to be risking a £50,000 penalty on a contract or whatever. So what would be a better way of sending the message? Well, maybe now I send the message, instead of just yes being a 1, maybe I'll send 3 1s, meaning a yes, and a no, meaning being 3 zeros. Well, now, what was the probability that I actually said no, don't sign? The probability that I said no, if she receives yes, is what? Well, each of these 3 must have gone from a 0 to a 1. So actually the probability is going to be a quarter, I hope, times a quarter, which is 1 over 64. So she can, with much more certainty, assume that if she receives 111, I didn't actually say no, I actually said yes, because each of these 3 must have changed. And so with these sorts of ideas, you can develop much more complex error-correcting codes. There's a whole theory of coding. There's also the whole theory of ciphers, sending secret messages, but it's a slightly different thing. Coding is encoding a message and sending it in a way that you can decode it at the other end. Ciphers are where you encode a message, but you also make it secret, so whoever's looking at it at the other end. In the States, I believe, the biggest employer of mathematicians is the National Security Agency. One of my graduates has just gone off to work at GCHQ. So why have they employed him? They've employed him because they need mathematicians to work out how to listen in on your mobile phone networks and that sort of thing. OK. So, possible careers. Right. It doesn't matter if you don't know what you want to do yet. How are we doing for time? Perfect. Doesn't matter if you don't know what to do yet. OK? Mathematics graduates are very much in demand. And a maths degree is about as good a non-vocational degree as you can find. So a vocational degree is something like law, medicine, accountancy, those sorts of things. You know pretty much you're going to go and become a doctor, a lawyer, an accountant. Mathematics degree, you don't know yet what you want to do. Maybe you do know, but you need a mathematics degree to do it. But if you don't know, it doesn't matter. You can look at prospects.ac.uk and moremathsgrads.ac.uk for lists and lists of careers and salaries and that sort of thing. More information than you can shake a stick at. And this is a quote from the ex-president of Exxon, the petroleum company, the research and development president. So he said, too few people recognise that the high technology so celebrated today is essentially a mathematical technology. This wouldn't work without mathematics. This wouldn't work. Your mobile phone wouldn't work. Actually, probably the paint that you paint the paint that I'm going to be painting my new walls with to get rid of the ghastly wallpaper that's in the house that I bought is going to have been designed by some point. Some mathematicians will have had their input into these things. So, possible careers. OK, so this is my list of careers that I kind of arranged. So, the sort of professional things, accountancy, actuarial, law, teaching, things where you need to go on after university to gain something. We can see why accountancy is sort of mathematical because it's sort of big sums or something. Actuarial work, you're trying to work out the probabilities that somebody who smokes but doesn't drink should have this sort of insurance, life insurance, or that sort of insurance. Those sorts of things, so statistical analysis. You can do law conversion courses. Why? Because you understand logical arguments, difficult technical arguments. You're good at understanding those things. Obviously, teaching as well. One of the most satisfying things is when your good students want to go and become teachers, okay? Because they're there to create the next generation of mathematicians, to inspire them. Civil service, scientific civil service, or just general civil service. If you want to go into the civil service, general civil service, you have to take a test. You have to take a literacy test and a numeracy test. Typically, my niece, who's a historian, really flunked the numeracy test. Other people who've had a maths degree breeze through that bit. The numbers, the mathematical side of it, becomes very easy if you have a maths degree. Management, company directorships. Why is maths good for management? Well, things like optimising profit. What's the best way for Sainsbury's to send its lorries around the country so that it saves fuel, makes the deliveries on time? How do you manage your stock control? Those sorts of things. Banking, share trading, backroom programmers. I wrote down this thing. So this is the Black-Scholes equation. This is what governs. So V is a derivative. Okay. What's a derivative? Well, a derivative is a financial instrument based on some asset. Okay. What does that mean? I'm not really sure. But here's an example of sort of the idea that it might be. So we have a farmer. Well, so a farmer and a miller, and the farmer agrees that in 6 months' time he will sell some wheat to the miller at a particular cost, and they agree that now. So they create a futures contract. Why is that good for them? Well, the farmer knows he has secured a sale, and the miller knows he's secured some supply. So he can make flour and sell it on to other people. And he may agree to sell flour to Sainsbury's or Tesco's or whatever after that. So, well then, there's this agreement. There's a contract between them. But actually you can start... So possibly the reason the banks got in such dangerous territory, because then they started doing things like taking that contract and selling that contract on to other people. And maybe hedging the bet so that because what can happen? Well, maybe there's a bad harvest and the farmer doesn't get any wheat at all, so he can't sell anything. Maybe there's a bad harvest, the farmer gets the right amount of wheat for his sale, but because there's a bad harvest, wheat is much more expensive than he was expecting it to be, so he's lost out a lot of money. Maybe the miller goes out of business and can't afford to pay him when the time comes anyway. So there are all sorts of risks associated with this, so you might want to hedge your bets. And that process of hedging and so on, these are where we start having derivatives, these financial instruments, the hedges, the agreements, the futures contracts, selling the contracts on the assets, the wheat. So this is the equation that Blacks and Scholes developed to explain how these things work. And so we've got this derivative here, this weird financial instrument, and it's going to vary, its value is going to vary with respect to time and with respect to the value of the stock, how expensive wheat is. And so this is the rate of change of this derivative with respect to time. This is the rate of change, the acceleration of the value of the derivative with respect to change in the value of the stock. This is the change in value of the stock. Here's the, for what it's worth, the interest rate, which is almost nominal these days, which is good for me because I've got a fixed rate mortgage, hurrah. And this one was something else that I can't remember now. The volatility of the stock. So we have this bizarre equation here which governs the markets. So what these banking guys are doing is building models of the economy with which to make huge amounts of money. And hopefully those models work. If they don't work, if their assumptions are slightly wrong, then we can end up in trouble. Okay, but a lot of mathematics going on there. Obviously, if you've got a maths degree, you can develop software, you know a lot about computing, that sort of thing. You can do research, what I do, so mathematics, statistical research, defence research, we mentioned, security, so people working in GCHQ, medical research, so understanding the risks of drugs, interpreting drug trials, that sort of thing. Sports research, when Joe and when I was first here, Joe had been here a while, one of our colleagues, Steve Otto, was increasingly interested in golf, and he now works for the Royal and Ancient Golf Club in Scotland, and he spends his days cutting golf balls in half, hitting golf balls very hard against walls with golf clubs and that sort of thing. Why? Because golf is a multi-billion-pound industry, and if somebody brings out a new golf club and claims it does something and can get Tiger Woods to use it, they will make huge amounts of money. There are rules associated with golf. For example, the dimples on a golf ball have to be evenly spaced. Mathematically, we know that's impossible. You can't evenly space them. You will get some points where the pattern degenerates and you get a hole. Same as the reason why you get a tuft of, whatever, sort of tuft patch where your hair cycles the wrong way. So we know it's impossible to evenly space them. So how can we mathematically think about that to say that actually they are evenly spaced or they aren't evenly spaced? Transport. How and where do you put bus stops? How and where do you run your traffic lights? That sort of thing. Aviation. How do you design an aeroplane? Telecommunications, we just spoke about. Computing, all of these things are mathematical. Scientific, technical consulting, obviously, so even if you're not doing research, you might understand enough mathematics to go in and tell people how to run their business, how to work out, analyse their data, analyse medical statistics, economics, that sort of thing. Meteorology. A few years ago, we had a chap here, graduate. He ended up working for a small company near Cambridge, and they were studying weather patterns on Mars to see if they could identify where the Beagle 2 spacecraft had landed a little bit more accurately, so they might have been able to ping it into life. We've had people go on into the forces, aircraft pilot, hairdresser, milkman. So that was my random list. I believe the hairdresser wanted to be a hairdresser. I'm not convinced the milkman actually set out to be a milkman. I may be wrong. So roughly speaking, this is just graduates from the University of Birmingham. This is sort of pie chart of where they ended up going to. This sort of data is always a little bit old, but roughly speaking, you can see for us, we have about 35% going into financial services. Teacher training is about 10%. Postgraduate degrees about 10%. So it's roughly the same as the sort of national average. And then the other will include the milkman and the pilot and the hairdresser. So how are we doing? A few more minutes. Let's do one more example of where... this is something I heard on the radio the other day, which I thought was fascinating. I need a clean board. So this is some research that Nick Clegg was quoting. It's about social mobility. So there's a graph by a chap, Leon Feinstein, did some research into social mobility. So what he did was he looked at the performance of various children and tracked it through over the years until they got to the age of 10. So he, 22 months, about 40 months. There was one other point, but just two. And then followed their performance through to 10 years old. And so this is, roughly speaking, a test performance. Think of it, maybe IQ. I'm not sure it was exactly IQ. And so he looked at kids from, roughly speaking, as the chap on More or Less on the radio said, this was not how he put it in his paper, but roughly speaking, smart rich kids, stupid rich kids, smart poor kids, stupid poor kids. And if you look at the graph, you start with, let's have some colours here. Smart rich kids, where's my graph? So they sort of start up really well, and the smart rich kids Smart rich kids come down like this, and then they sort of amble across like that. Smart, what shall I do next? Dim rich kids kind of start like this, and they sort of carry on up like that somehow. Smart, dim, stupid, so this is smart, no, this is rich, dim. Tim, nice but dim. There we go. Here's rich, smart. And here's poor dim, which is all, you know, worrying because rich dim and poor dim are different and so on. But the really worrying one for the government is this one, which is poor, smart. Okay, so some very worrying data. If you're rich, this seems to say, if you're rich but stupid, you will at some time overtake poor but smart kids, according to these tests. And this sort of data, this informs government policy. Should worry all of us, right? Because what's happening is we're losing really smart kids who could be contributing to the economy, who could be the next Einstein or whatever. So, fine. And this data's been taken as very fundamental in the way we should form policy, both by Labour Party and the Liberal Democrats and the Conservatives. The programme I was listening to on the radio said that actually there's a statistical process that goes on here, which is called regression to the mean, which might be at least exaggerating this data. Maybe it's not quite as so awful as we might expect. And it goes like this. So at 22 months, you take a bunch of kids and you test them. And then you look at the really smart ones, the ones who do really well on the test, rather, and you look at the ones who do really badly on the test. And then you test them again, and then you test them again. All the middle kids, you leave out. But think about what's happening here. So we're taking a bunch of kids, right? And you test them. Well, maybe you've got a really smart kid who just had a bad day. Maybe he had a headache. Maybe he was unhappy because his mum had left him at school and he wanted to go to the playground, whatever. They're only 22 months old, after all. So really smart, poor kid has a bad day, so he comes out somewhere in the middle. Maybe some average kid flukes the questions and gets a really high score. So think about it like you go to a restaurant. Let's go to a restaurant. Do we like the food? Yes. OK, so are we going to rate that restaurant as an excellent restaurant today? OK, so let's rate it as an excellent restaurant. You go back in a few months' time to the same restaurant and actually it wasn't as good. Well, why was that? Well, maybe they had a temporary chef in who was a really good chef. Maybe the chef's left. Maybe it was just a very good day. Maybe you chose well on the menu, and when you chose something else, it turned out they couldn't cook at all. All they could cook was macaroni cheese. So this is called regression to the mean. You choose your sample of really good students on one showing. Some of them weren't really good. Some of them were just average, but they did well on the day. Bad teams can sometimes win the FA Cup, right? On average, they don't, but from time to time, a not very good team can beat a very good team. It just happens. So when you discount that sort of effect, this thing here becomes less obvious. OK, that sort of argument, that kind of subtle argument looking deeper into the data, that requires what? That requires some statistical knowledge which you've learned at some higher level, and it also requires the ability to understand those arguments. So you need to have had some prior knowledge. You need to have seen that somewhere or other, and you need to understand it because probably you've seen it now in this respect, but actually can you apply it to the restaurant trade? Can you apply it to other things? So that sort of ability to apply your knowledge in novel situations is another thing that you learn in a maths degree. And here, hopefully, I've explained it so you get some vague inkling of what's going on, because part of the idea is to be able to explain this to government ministers to say, well, maybe the picture isn't quite as simple as we expect. Now, I should point out, the guy who was saying this regression to the mean, that this picture might not be as disastrous for the country as we think, he still said there was definitely, you definitely have an advantage if you're rich rather than you're poor, but that the graph that Feinstein did, and Feinstein doesn't necessarily agree with this, but the graph was not so dramatic. Okay, so, bit of stats. Evidence and proof, well, okay, so we've had some evidence and proof. Why is maths good for a career? Relative earnings. You saw how much more you earned with a mathematics degree than an average degree. Therefore, you have greater social mobility. You are able to move between jobs and so on. Wall Street Journal. You can look this up, Google it. Wall Street Journal, list of best and worst jobs. How are we doing for time? 2 minutes? OK, so I won't pick it up now. So the best job is software engineering, according to the Wall Street Journal survey. They do this every year. The second best is being a mathematician. In the top 10, pretty much half of them at least are to do with mathematics. The 150th best job that they did out of the 200 was cleaning up nuclear waste. So it kind of made me think of all those poor guys in Fukushima. The worst, or the second to worst, was lumberjack. The worst was kind of handyman, actually. So there we go. So 2004 figures, I stole these from Michael. 61% of maths graduates entered employment, and a further 23% went on to further study. Okay, so there you are employable. 84% going into jobs or further study. And probably I think we'll leave it there. I was going to say, what do we need to study maths? So I've been talking about these things. Let me just pull all of this up. Okay, the important thing here is I think maths, like music, like sport, is very easy to spot the guys who are really good. The person who can sit down at a piano and play blues, Bach, Beethoven, just like that. Yeah? The guy who just clearly runs rings around everyone else on the football pitch. The Johnny Wilkinsons and so on. The guys who sit, in your class, you know who they are, who are just really, really good at maths. Maybe it's you guys here. But actually, I think one of the important things about maths is not just for those frighteningly brilliant people. Okay? I know a lot of mathematicians. I don't know very many brilliant people. Most of us just work hard at something that we really love. So maths is not for the brilliant only. It's for the people who are good at mathematics. So the people who are aiming to get A's and B's in A-level maths. What you do need to know is you want to know why. You want to know why things like that is true. The 5 most significant numbers in mathematics, all related by one amazing formula. OK, so that's the end of my talk. I hope I've shown you that maths is at least involved in something. You've had a fairly tough day so far, so I think with a bit of fun now, Joe's going to award some prizes.
But I think first a round of applause for...